Hello, friends. Welcome back. Or if this is the first time you found your way here, welcome. I'm so glad you're here tonight. Right now, at this very moment, the space beneath your feet, the floor, the ground, the earth itself, is vibrating at a level so small, so impossibly tiny, that no instrument on Earth has ever directly seen it. And yet, physicists believe it's real. They believe that what we call empty space, the nothingness between stars, the silence between atoms is not still at all. It is foaming. Before we begin tonight's journey, if these quiet explorations of the universe bring you some peace, some wonder, some company in the dark you might like to stay a while, you can gently tap the like button, let it rest there like a small light left on. And if you'd like more nights like this, subscribe not for the noise, but so the next quiet evening can find you again. The little bell is there too soft and patient waiting. Now, let's drift. Tonight we are going somewhere most people never think to look, not outward to distant galaxies, not deep into the ocean's floor. We're going smaller, much, much smaller, down past atoms, past protons, past quarks, to a place where space itself stops behaving the way we think it should. A place where our most elegant theories break down, where physics gets strange and beautiful and deeply, profoundly unsolved. Tonight we ask a question that sounds almost too simple to be serious. Is space actually smooth? You've probably never questioned it. Why would you? Look around you right now. The air between your hand and the wall across the room, it seems empty, calm, uncomplicated. Space in our everyday experience is just there, a container, a stage on which things happen. We move through it without friction, without resistance, without drama. It does not resist. It does not push back. It simply holds. And for most of human history, that was enough. The ancient Greeks imagined space as a kind of infinite void, a divine emptiness that the universe was carved into. Aristotle believed a perfect vacuum was impossible, that nature itself would rush to fill any empty space. He called it horror vacui, the horror of the void. It sounds almost poetic now, but he wasn't entirely wrong about one thing: space is never truly completely empty. He just couldn't have imagined why. For centuries, natural philosophers debated the nature of the void. Was it nothing? Was it something? Could nothing even exist? René Descartes in the 1640s argued that space was identical to matter, that the very extension of space and the extension of physical objects were one and the same thing. There could be no space without substance, he believed. No room without walls. Then came Isaac Newton. And Newton did something bold, something almost controversial for his time. He insisted that space was absolute, fixed, infinite, a kind of cosmic framework, unchanging and indifferent, through which planets and comets and falling apples all moved. Space to Newton was the universe's great stage, and the stage was not part of the play. It simply existed serene and featureless, a backdrop of pure geometry stretching in all directions forever. For over 200 years that view held. And honestly, it was magnificent in its clarity. Newtonian space was elegant. It was predictable. It gave us the mathematics to launch cannonballs, to calculate tides, to eventually, centuries later, send rockets to the moon. But it was wrong, or at least incomplete. In 1905, a young patent clerk in Bern, Switzerland, published a paper that would quietly rearrange everything. Albert Einstein showed that space and time were not separate, independent things. They were woven together into a single fabric he called Spacetime. And in 1915, he went further, still showing in his general theory of relativity that this fabric was not rigid at all. It could bend. It could curve. A massive object like the sun didn't just sit in space, it warped the space-time around it, the way a bowling ball rests in the center of a stretched rubber sheet. This was revolutionary. Space was no longer Newton's passive stage. It was an active participant in the story of the universe. It flexed and curved in response to mass and energy. Black holes were places where space-time curved so sharply It essentially folded in on itself. Gravitational waves were ripples in the fabric of space-time, spreading outward like rings in a pond when a stone breaks the surface. And yet, even in Einstein's vision, space-time was smooth, continuous. It curved, yes, like a sheet of rubber, but rubber is smooth. You could zoom in as close as you liked, and in principle, the geometry would remain well-behaved, ordered, differentiable in the language of mathematics. Einstein's space-time was beautiful precisely because of this smoothness. It was a clean, elegant, continuous surface on which the universe painted its story. But then came quantum mechanics. And quantum mechanics, as it tends to do, complicated everything. Through the 1920s and 1930s, physicists built a new picture of reality, one where particles didn't have definite positions until they were observed, where energy came in discrete packets called quanta not smooth flowing streams, where nothing could be known with perfect precision because precision itself was forbidden by the laws of nature. This was the world of Heisenberg, Bohr, Schrödinger, Dirac, a world of probability, uncertainty, and strange quantum weirdness. And here is where the story gets truly interesting, because quantum mechanics and general relativity, the two greatest achievements of 20th century physics, cannot both be right at the same time. When you try to apply quantum mechanics to gravity, when you try to quantize space-time, the way physicists quantized light and electrons, the mathematics collapses. You get infinities where there should be numbers. You get predictions that make no physical sense. The two theories, each extraordinarily successful in its own domain, are fundamentally incompatible at the deepest levels. Physicists sometimes describe this as one of the greatest unsolved problems in all of science. We have two instruction manuals for the universe. One works perfectly for the very large galaxies, black holes, the expansion of the cosmos. The other works perfectly for the very small atoms, photons, the behavior of subatomic particles. But when you try to use both manuals at the same time, the pages tear. Have you ever tried to fit two puzzle pieces together and they just won't connect? Not because they're wrong, but because they're from two completely different puzzles. That's something like where physics stands today. And at the heart of this incompatibility is a question about the nature of space itself. Is it smooth all the way down, or does it at some impossibly small scale become something else entirely? Something granular, something turbulent, something that foams. The scale we're talking about is called the Planck length, named after the German physicist Max Planck, who in 1900 introduced the idea of quantized energy, a discovery he reportedly found so disturbing that he initially hoped someone else would come along and prove him wrong. The Planck length is approximately 616 times 10 to the negative 35 meters. That number is difficult to truly absorb. Let's try to feel it gently. A single human hair is roughly 100 micrometers wide, about 1/10 of a millimeter. If you took that hair and divided it into 1,000,000 equal pieces, each piece would be about the size of a large atom. Now, take that atom and divide it into 1,000,000 pieces again. You're approaching the size of a proton. Now, divide the proton into 1,000,000 pieces, then 1,000,000 again, then 1,000,000 more times after that. You still haven't reached the Planck length. The Planck length is so small that the very concept of distance, the idea that you can draw a line between 2 points, may cease to have meaning below it. Space as we know it might simply stop making sense at that scale. And according to a theory first proposed in 1955 by one of the most remarkable physicists of the 20th century, a man who had sat beside Einstein, who had helped design the first plutonium bomb, who would later invent the term black hole at the Planck scale, space is not smooth at all. At the Planck scale, space foams. His name was John Archibald Wheeler, and the idea he proposed, this notion of quantum foam, was not just a metaphor. It was a physical hypothesis grounded in the principles of quantum mechanics. It was in its way the universe whispering that its foundations were stranger than any of us had imagined. But to understand why Wheeler proposed this, why he believed that the very fabric of space was seething with energy and uncertainty at the tiniest scales, we need to go deeper. We need to meet the principle that made it possible. The principle that says uncertainty is not a flaw in our instruments, not a limitation of our knowledge, but a fundamental feature of reality itself. And that story begins with a young German physicist standing at a blackboard in Copenhagen in the winter of 1927, writing equations that would change what it meant to know anything at all. Werner Heisenberg was 25 years old when he wrote the equation that broke physics, not broke it in the way a machine breaks grinding to a halt, sparks flying, something obviously wrong. Broke it the way a mirror breaks suddenly, irreversibly, and with the unsettling realization that what you were looking at was never quite what you thought it was. The winter of 1927. Copenhagen. The Niels Bohr Institute, a quiet cluster of buildings near the center of the Danish capital, had become the unlikely center of the universe's most intimate secrets. Young physicists from across Europe gathered there, the way musicians once gathered in Vienna, drawn by something electric in the air, something unfinished and urgent and alive. Heisenberg had been wrestling with a deceptively simple problem. When you observe a particle, say, an electron, you want to know two things: where it is and how fast it's moving. Position and momentum. These seem like the most basic facts you could ask about any moving object. You ask them about cars. You ask them about planets. You ask them about baseballs. But electrons, Heisenberg discovered, would not cooperate. The more precisely you tried to pin down an electron's position, the more uncertain its momentum became. And the more precisely you measured its momentum, the more its position blurred and smeared into a kind of probabilistic haze. This was not a problem with the instruments. It was not a problem with the physicist's eyesight or steadiness of hand. The uncertainty was written into the fabric of reality itself. He called it the uncertainty principle. And when he showed his equations to Niels Bohr, even Bohr, one of the architects of quantum mechanics, reportedly paced the room in silence for a long time before speaking, because what Heisenberg had found was not a technical limitation. It was a statement about the universe. Reality at its most fundamental level does not have sharp edges. It does not have definite values waiting to be discovered. An electron does not have a precise position and a precise momentum at the same time, not because we can't measure both, but because both do not simultaneously exist. Let that settle for a moment. Not because we can't know, because it isn't so. Now, here is where the story takes a turn toward the strange and beautiful. Because Heisenberg's uncertainty principle doesn't only apply to particles, it applies to energy and time as well. And this second form of the principle, the energy-time-uncertainty relation, has consequences so extraordinary, so counterintuitive that they reach all the way from the subatomic world to the structure of space itself. The energy-time version of the principle says this: the shorter the time interval you examine, the less certain the energy within that interval must be. In other words, over very brief moments of time, energy is fundamentally indeterminate. It fluctuates, it shimmers, and these fluctuations are not errors. They are not noise in the signal. They are the signal. This means that even in a region of space that contains nothing, no particles, no radiation, no matter of any kind, energy is still there flickering in and out of existence. The vacuum, it turns out, is never truly empty. It seethes with what physicists call quantum fluctuations, a kind of invisible restless energy that hums beneath everything everywhere always. Now here is a question worth sitting with for a moment. If energy can fluctuate in empty space, if the vacuum itself is alive with invisible motion, what does that mean for space itself? This is the question that John Archibald Wheeler asked in 1955. And to understand why his answer was so remarkable, you need to know something about the man himself. Wheeler was born in 1911 in Jacksonville, Florida. By the time he was in his early 20s, he had already earned his doctorate in physics from Johns Hopkins University. He was not a loud man, not a showman. He was quiet, precise, deeply thoughtful, the the kind of person who chose words the way a jeweler chooses stones, carefully with attention to weight and clarity. He studied under Niels Bohr in Copenhagen, the same Copenhagen where Heisenberg had spent those formative winters. He worked alongside Enrico Fermi on the Manhattan Project, contributing to the theoretical design of the first nuclear reactors. He collaborated, corresponded, and argued respectfully with Albert Einstein in Princeton, where both men spent significant portions of their careers. Einstein and Wheeler had a complicated intellectual relationship. Einstein never fully accepted quantum mechanics. He famously believed that God does not play dice with the universe, that the apparent randomness of quantum theory was a symptom of our ignorance, not a feature of reality. Wheeler, who admired Einstein enormously, did not share this conviction. Wheeler believed the dice were real. He believed uncertainty was fundamental. It was this conviction and his deep familiarity with both general relativity and quantum theory that led Wheeler to a startling idea. He knew from Einstein that mass and energy curve space-time. A star warps the geometry of space around it. A black hole warps it so severely that space itself becomes a one-way door. The larger the energy, the more dramatic the curvature. And he knew from Heisenberg that energy fluctuates especially over tiny distances and tiny time intervals. The smaller the scale, the larger and more violent the fluctuations. So, Wheeler asked what happens when you take the energy fluctuations of the quantum vacuum and apply them to space-time geometry. If energy curves space-time and energy is fluctuating wildly at the smallest scales, then space-time must be fluctuating wildly at the smallest scales too, not curving gently the way a massive star curves it, churning, frothing, distorting into wild tangled shapes that appear and disappear faster than any clock could record. Wheeler called this quantum foam, and the scale at which this foaming would occur, the Planck scale, is so incomprehensibly small that the universe we see with its smooth stars and quiet voids and gently curving space-time is a kind of average, a smoothed-out composite, like how the surface of the ocean looks calm and flat from 30,000 feet. Even when up close, it is churning with waves and currents and endless motion. The image Wheeler offered was vivid and strange. Imagine taking a photograph of a stormy sea from a great distance. The surface looks relatively smooth, a slight undulation, nothing dramatic. Now, zoom in, closer, closer still. Suddenly you see waves, then whitecaps. Then the chaotic froth where wave meets wave. At the very smallest scale, the water is in violent, turbulent, almost incomprehensible motion. Space Wheeler proposed is the same. From the scale of everyday life, from the scale of atoms, even it appears smooth and well-behaved. But zoom in to the Planck scale and you would see something utterly different. Tiny wormholes flickering in and out of existence. Loops of distorted geometry forming and dissolving in intervals so brief they have no name in any human language. A roiling, seething topological chaos where the concepts of here and there and before and after lose their ordinary meaning. It is worth pausing here to appreciate the intellectual courage this required. In 1955, quantum field theory was still young. The tools to calculate the behavior of quantum fluctuations in curved spacetime didn't fully exist. Wheeler was not writing down a set of equations that could be immediately tested. He was doing something that physicists sometimes describe with mixed admiration and suspicion as theoretical speculation, reasoning from first principles toward a conclusion that felt right, that felt necessary, even if it couldn't yet be proven. And here is something that often gets misunderstood about this kind of physics speculation in the hands of someone like Wheeler is not guessing. It is a disciplined act of imagination, constrained by mathematics and physical law. Wheeler was not saying, perhaps space is foamy, because it would be interesting if it were. He was saying, given what we know about quantum mechanics and given what we know about general relativity, this is what the mathematics seems to require. The mistake many people make, and it's an easy one, is to assume that because quantum foam has never been directly observed, it is somehow less real than things we can see and touch. But many of the most real things in physics have never been directly observed. We have never seen a quark in isolation. We have never watched two gravitational waves collide in real time. We have never directly imaged the event horizon of a black hole from the inside. And yet we believe in quarks. We detected gravitational waves indirectly at first then, with extraordinary precision at LIGO in 2015. We photographed the shadow of a black hole, not the thing itself, but its effect on everything around it. Evidence in physics is often indirect, and sometimes the most important ideas live for decades in the space between mathematics and measurement, waiting for instruments to catch up with imagination. Wheeler spent the rest of his long career, he lived to 96, dying in 2008, wrestling with the deepest questions about the nature of reality. He was the man who coined the term black hole, giving a name to something that had previously existed only in equations. He coined the phrase "it from bit," suggesting that at the deepest level, the universe might be made not of matter or energy, but of information. He was in every sense a man who thought at the edges of what was knowable. And the concept of quantum foam, this strange, unsettling image of space as a restless, frothing sea at the smallest scales, remained one of his most enduring contributions. Not because it has been proven, but because it asks the right question in the right way, pointing toward a gap in our understanding that the greatest minds in physics have spent decades trying to cross. Think about that for a moment. The smooth, quiet space you are resting in right now, the air around you. The silence between walls may be at its deepest level, anything but smooth. It may be a kind of organized chaos, an average of unimaginable complexity. A surface tension, holding beneath it a reality that has no name in any ordinary language. But Wheeler's foam is not just a poetic image, it is rooted in specific calculable physics. And to understand why physicists take it seriously, why some of the most rigorous and skeptical minds in science have dedicated careers to exploring it, we need to go to the place where the foam originates. We need to understand what actually happens when energy fluctuates in empty space, and why those fluctuations are not just theoretical shadows, but leave measurable, detectable fingerprints on the physical world. Because in a small laboratory in the Netherlands in 1948, a Dutch physicist sat down with a set of equations about the vacuum, about the energy of nothingness, and predicted something that, when finally measured, would change the way science understood emptiness forever. That Dutch physicist's name was Hendrik Casimir, and what he predicted and what was later confirmed in the laboratory with extraordinary precision was that two uncharged metal plates placed close enough together in a perfect vacuum would be pushed toward each other by nothing. Not by gravity, not by magnetism, not by any known force acting between them, by nothing, by the vacuum itself. This is not a thought experiment. This is not a metaphor. This is a measured, reproducible, experimentally verified phenomenon that sits quietly in the literature of physics, like a small, polite miracle, the universe's way of reminding us that emptiness has a texture we do not fully understand. To see why Casimir's prediction matters, why it reaches all the way to the question of quantum foam, and the nature of space, we need to spend some time in the vacuum. Not the vacuum of a cleaned carpet or an airless room. The quantum vacuum, the deepest possible emptiness that physics allows. And here is where almost everyone's intuition leads them astray. When most people hear the word vacuum, they imagine absence, a container with everything removed, a space where nothing happens because there is nothing there to happen with. The perfect vacuum in the everyday imagination is the perfect 0-0, matter zero, energy zero activity. But quantum mechanics forbids this. And it forbids it for a reason we have already begun to glimpse Heisenberg's uncertainty principle. Recall what the energy-time version of the uncertainty principle tells us. Over very short time intervals, energy cannot be precisely defined. It must fluctuate. It must be uncertain. And because this is a law of nature, not a suggestion, not an approximation, but a hard constraint on reality, It applies everywhere at all times, including in the supposedly empty vacuum. What this means in practice is both beautiful and deeply strange. The quantum vacuum is filled with what physicists call zero-point energy, a kind of irreducible, ineradicable background hum of energy that cannot be removed even in principle. You cannot cool the vacuum down to zero energy. You cannot extract this energy and leave true nothingness behind. The fluctuations are permanent. They are intrinsic. They are in a very real sense what the vacuum is made of. And these fluctuations are not abstract. They are physical. They manifest as pairs of particles, a particle and its antimatter partner that flicker into existence together, exist for an almost unimaginably brief moment, and then annihilate each other and vanish. In the language of quantum field theory, these are called virtual particles. And while virtual might sound like not real, the word is misleading in exactly the way that matters most. Virtual particles are real in the sense that they have measurable consequences. They affect the behavior of real particles. They contribute to observable phenomena. They are not a bookkeeping trick or a mathematical convenience. They are participants in the physical world, even if their participation is brief and invisible. Now here is what Casimir realized in 1948. If the vacuum is filled with fluctuating quantum fields with virtual particles appearing and disappearing in a constant restless churn, then those fluctuations extend throughout all of space. They fill every region of the vacuum with a kind of invisible energy spectrum, a continuous range of wavelengths humming at all frequencies simultaneously. But if you place two parallel metal plates very close together, close enough that the gap between them becomes comparable to the wavelength of these vacuum fluctuations, something interesting happens. The space between the plates is too small to accommodate all the wavelengths that exist in the open vacuum outside. Long wavelengths simply cannot fit. They are excluded. The result is that the energy density of the vacuum inside the gap is slightly lower than the energy density outside. And lower energy inside than outside means just as surely as a higher pressure. Outside a sealed container pushes inward, the plates are pushed together. Not by any particle hitting them, not by any classical force, by a pressure difference in the vacuum itself. Casimir calculated the magnitude of this force. It was tiny, extraordinarily tiny, but it was specific and it was testable. For two plates separated by 10 nanometers, roughly 100 times the diameter of a hydrogen atom, the Casimir force is equivalent to about 1 atmosphere of pressure. Significant enough to measure. For decades after Casimir's 1948 paper, the experimental technology to test his prediction precisely enough simply didn't exist. Physicists believed the effect was real, but the measurements were noisy, inconsistent, difficult to interpret. Then in 1997, physicist Steve Lamoureux at the University of Washington measured the Casimir force directly with an accuracy of about 5%. In 2001, further experiments brought that accuracy to within 1%. The vacuum pushed, exactly as predicted. The nothingness between the plates exerted a measurable, calculable force on the physical world. This is worth sitting with for a moment, because what the Casimir effect confirms is not just a quantum curiosity, it confirms that the vacuum is not nothing. It has structure, it has energy, it responds to geometry. Change the shape of the space, and you change the energy of the vacuum, and that changed energy produces a real physical force. And if the vacuum has structure, if it responds to the geometry of the containers we build around it, then it is not unreasonable to ask what happens when the geometry in question is not a pair of metal plates, but space-time itself. This is precisely the leap that connects the Casimir effect to quantum foam. Wheeler's intuition that space-time at the Planck scale must be frothing with violent quantum fluctuations is essentially the Casimir argument applied to the fabric of the universe itself. If vacuum fluctuations respond to the geometry of space, and if geometry itself is subject to quantum uncertainty at the smallest scales, then geometry must fluctuate too. Space-time must foam. Think of it this way. Imagine the surface of a drum. When you strike it, it vibrates, waves move across the surface, the membrane flexes and bounces and eventually settles. Now imagine that the membrane itself has a temperature. At the molecular level, even a still unstrucken drum is vibrating. The molecules of the membrane are in constant thermal motion, too small and too fast for you to see, but real. The surface looks still. It is not still. It is an average of constant motion. Quantum space-time is something like this. What we see smooth, continuous, well-behaved geometry is an average, an emergent calm. At the scale of Planck length, the geometry is doing something far more dramatic, something that bears no resemblance to the smooth space-time of Einstein's equations. Now, here is a common misconception worth addressing directly because it comes up often and it matters. When physicists talk about quantum foam, some people imagine it as a kind of literal foam like soap bubbles, fixed structures floating in space. But this image, while evocative, misses something important. Quantum foam is not a static structure. It is a dynamic, constantly changing pattern of fluctuations. The bubbles, if you want to call them, that are not objects. They are events. They flicker into being and out of being at time scales so short that the word brief is itself inadequate. We are talking about intervals of roughly 10 to the negative 43 seconds called Planck time, the shortest meaningful duration that current physics can define. At that time scale, our ordinary notions of before and after of cause and effect may not apply. The quantum foam is not a place you could visit even in principle. It is a regime where the very coordinates we use to describe location and duration dissolve into uncertainty. And yet, and this is the part that physicists find both thrilling and frustrating, even though we cannot see it, even though no instrument we have built can probe it directly, the quantum foam may leave traces. It may influence the universe at larger scales in ways that are in principle detectable. One of the most intriguing possibilities involves light. Specifically light that has traveled a very long way. When light travels through a smooth, featureless vacuum, all wavelengths travel at the same speed. That is a foundational fact of special relativity. But if space-time is not smooth, if it has a granular, foamy texture at the Planck scale, then different wavelengths of light might interact with that texture differently. High-frequency photons with shorter wavelengths might be more sensitive to the microscopic roughness of space-time than low-frequency photons with longer wavelengths. The result would be a tiny difference in travel time high-energy light arriving fractionally later than low-energy light, even though both began their journey at the same moment. Over short distances, this difference would be completely undetectable, but the universe is vast and light. From distant explosions, gamma-ray bursts travels for billions of years before reaching us. A tiny difference in speed accumulated over billions of light years might become measurable. This is exactly what NASA's Fermi Gamma-Ray Space Telescope has been designed in part to look for. And we will come to Fermi's results and what they do and do not tell us about quantum foam in the chapters ahead. But before we get there, we need to sit with something that the Casimir effect reveals about the relationship between mathematics and reality. Because there is a lesson here that goes beyond particle physics. Casimir derived his prediction from a set of equations about the quantum vacuum. Those equations told him that something measurable should happen, that two plates should be pushed together by the energy of nothing. And for nearly 50 years, physicists trusted those equations even without experimental confirmation, because the mathematics was sound and the physical reasoning was clear. This is not blind faith. It is something more interesting, a kind of disciplined confidence in the internal consistency of a well-tested framework. Quantum field theory. The broader theory within which the Casimir effect sits had made dozens of other predictions that were experimentally confirmed. Its track record earned it a kind of provisional trust. Have you ever wondered how science decides what to trust when it can't yet test everything directly? This is precisely how. Not by testing every prediction individually, but by building frameworks theories whose internal logic is tight, whose other predictions hold up, and whose mathematical structure points toward new phenomena before the experiments can catch up. Wheeler's quantum foam sits in this same category. It has not been directly confirmed, but it emerges from the same quantum mechanical framework that gave us the Casimir effect, the Lamb shift, the anomalous magnetic moment of the electron, some of the most precisely verified predictions in the history of science. It inherits credibility from its neighbors. It is not proven, but it is not groundless. It lives in a neighborhood of ideas that has repeatedly turned out to be right. And there is something quietly extraordinary about that. The idea that the floor beneath your stillness tonight is at the deepest possible level, a churning sea of geometry, that space itself is not the passive container. Newton imagined not even the smooth rubber sheet of Einstein's relativity, but something alive and restless and profoundly uncertain. This idea does not come from imagination alone. It comes from equations that have been tested, refined, and confirmed over nearly a century of the most careful science humans have ever done. The vacuum pushed two metal plates together. That happened. That is real. And if emptiness can do that, if nothing can exert a force, then perhaps the question of whether space is smooth is not as settled as it seems. Because once you accept that the vacuum has structure, the next question is almost unavoidable. If the vacuum fluctuates and fluctuations curve spacetime, and spacetime is itself subject to quantum laws, then what exactly is spacetime made of? Is it continuous like the surface of a still lake, or is it at the smallest scale? Something more like a mosaic, a collection of discrete pieces so small that the joins between them are invisible from any distance we can manage. That question, the question of whether space-time is fundamentally continuous or fundamentally discrete, is one of the deepest in all of physics, and it sits at the exact boundary between the two greatest theories of the 20th century, both of them correct, both of them beautiful, and both of them, in a very specific and important sense, irreconcilable with each other. Two theories, both correct, both beautiful, both tested to extraordinary precision against the most demanding experimental standards in the history of science. And yet, when you try to make them speak the same language, they fall silent. This is not a small problem. This is not a gap that will be filled with a minor adjustment, a tweaked constant, a refined measurement. This is a fundamental structural incompatibility at the very foundation of physics. And understanding exactly where the conflict lies is essential to understanding why quantum foam is not just a poetic metaphor, but a genuine scientific crisis dressed in elegant mathematics. Let's begin with Einstein's side of the argument. General relativity, published in its complete form in November 1915, is one of the most beautiful theories in the history of human thought. Not beautiful in the way a painting is beautiful, beautiful in the way a proof is beautiful. Inevitable, internally consistent, spare. It begins with a single audacious idea that gravity is not a force at all in the classical sense. Gravity is geometry. When you place a massive object, a star, a planet, a black hole in space-time, it does not reach out and pull other objects toward it. It curves the space-time around it, and other objects moving through that curved space-time follow the straightest possible paths available to them, paths called geodesics. What we experience as gravitational attraction is simply the effect of following a straight line through curved space. The mathematics of general relativity is built on a branch of geometry developed in the 19th century by Bernhard Riemann, a shy, brilliant German mathematician who spent most of his career in Göttingen and died of tuberculosis at 39, never knowing that his abstract work on curved surfaces in multiple dimensions would one day describe the shape of the universe. Riemann's geometry assumes smoothness. It assumes continuity. It is a geometry of infinitely divisible space where you can always zoom in a little further and find more structure, more detail, more well-defined curvature. Einstein's general relativity inherits this assumption completely. Space-time in Einstein's framework is a smooth, continuous four-dimensional manifold. It can bend and stretch and warp in dramatic ways, but it never breaks. It never becomes grainy. It never loses its basic geometric character. No matter how close you look, at least in principle, it remains a well-defined surface with a well-defined curvature. This smoothness is not incidental. It is load-bearing. The entire mathematical structure of general relativity depends on it. The equations only work if space-time is continuous. If space-time is discrete, if it has a smallest unit, a quantum of geometry below, which the concept of distance loses meaning, then the differential equations at the heart of general relativity cannot be written down in their current form. The theory as it stands would need to be replaced by something more fundamental. Now, let's step across to quantum mechanics. Quantum field theory. The framework that describes all known particles and forces except gravity is built on a completely different set of assumptions. Where general relativity is a theory of smooth, continuous geometry, quantum field theory is a theory of discrete quantized interactions. Energy comes in packets. Angular momentum comes in packets. Particle interactions happen at points. Fields are operators that act on quantum states, not smooth functions defined on a classical background. And crucially, quantum field theory is formulated on a fixed flat background space-time. It treats space and time as a stage passive inert, unaffected by the quantum drama playing out upon it. This is precisely the Newtonian assumption that general relativity overthrew. Quantum field theory in its standard form does not know that space-time is dynamic. It does not know that gravity bends the stage. It works beautifully in weak gravitational fields where the curvature of space-time is negligible and the fixed background approximation is good enough. But in regions of extreme gravity near the center of a black hole or at the moment of the Big Bang, it breaks down completely. So we have general relativity, which requires smooth, continuous space-time formulated without quantum mechanics. And we have quantum field theory, which requires a fixed background space-time formulated without gravity. Each theory in its own domain works astonishingly well. The problem arises in the overlap in the regime, where both quantum effects and gravitational effects are simultaneously important. That regime is the Planck scale. At the Planck scale, the energy fluctuations of the quantum vacuum become large enough to significantly curve space-time. And the curvature of space-time becomes so extreme that quantum effects can no longer be ignored. The two theories are forced into conversation, and the conversation in the mathematical language currently available produces nonsense. The technical term for this is non-renormalizability. When physicists try to quantize gravity to apply the same mathematical procedure that successfully quantizes electromagnetism, the weak force and the strong force they get infinities. Not the manageable kind of infinities that appear in other quantum field theories and can be systematically removed through a procedure called renormalization. They get infinities that cannot be removed. The theory produces an infinite number of free parameters that would need to be fixed by experiment, an infinite number of measurements that would need to be made before any prediction could be extracted. A theory with infinite free parameters is not a theory. It is a placeholder. A flag planted in the ground that says something is here, but we don't yet know what it is. And this is where the question of whether space-time is smooth or granular becomes not just philosophical, but urgent. Because the most promising attempts to build a theory of quantum gravity, a theory that could describe physics at the Planck scale and reconcile general relativity with quantum mechanics, make very different assumptions about the nature of space-time at the smallest scales. Consider two of the leading approaches. String theory, developed through the 1970s and 1980s, proposes that the fundamental constituents of nature are not point particles, but tiny one-dimensional objects, strings whose different vibrational modes correspond to different particles. In string theory, space-time remains continuous, at least at scales larger than the string length, which is typically assumed to be near the Planck length. Gravity emerges naturally from string theory as the interaction mediated by a massless spin 2 particle called the graviton, which corresponds to a particular vibrational mode of the string. The foam in this picture is a consequence of string dynamics, a turbulent sea of strings and higher dimensional membranes at the Planck scale rather than a turbulent sea of space-time geometry. Loop quantum gravity takes a very different approach. Rather than replacing the point particles of conventional physics with strings, loop quantum gravity attempts to quantize space-time geometry directly. The result is a picture in which space-time itself is discrete, made of fundamental indivisible units of area and volume at the Planck scale. Space is not a smooth continuum, but a network, a web of interconnected nodes, each representing a quantum of volume, each connection representing a quantum of area. The foam in loop quantum gravity is not a fluctuation on a smooth background. It is the background. Space itself, at its deepest level, is a kind of quantum lattice. These two pictures could not be more different. And the striking thing is that as of today, neither has been experimentally confirmed. Both make predictions that go beyond current experimental reach. Both contain beautiful mathematics and profound physical ideas. Both have attracted some of the most gifted physicists of the past half-century, and both remain in the deepest sense unproven. Here is something worth pausing on. Have you ever considered what it means for two competing theories to both be beautiful, both be mathematically consistent, and both be beyond current experimental reach? In everyday life, when two explanations are both plausible, we look for more evidence. We run more tests. We design experiments to distinguish between them. But at the Planck scale, the experiments are extraordinarily difficult. The energies required to probe Planck scale physics directly are approximately 10 million billion times larger than those achievable at the Large Hadron Collider at CERN, currently the most powerful particle accelerator ever built. This is a situation physics has rarely faced before. Not a shortage of ideas, but a shortage of experiments capable of testing them. And yet, and this is important, the situation is not hopeless, because there are indirect approaches. There are ways to look for Planck-scale physics without building a Planck-scale accelerator. They are subtle, and they require patience, and they depend on some of the most extreme environments in the observable universe. But they are real, and they are being pursued, and some of them have already begun to return results. One of the most elegant involves a phenomenon that connects the smallest scales in physics to the largest distances in the observable cosmos. A connection so unexpected, so quietly astonishing, that it deserves its own careful telling. But before we get there, it is worth sitting with the central tension one more time. Einstein's space-time is smooth. Quantum mechanics demands fluctuation. Both are right. Both cannot simultaneously be right in the same regime. And the regime where they conflict, the Planck scale, is the scale at which Wheeler's quantum foam lives. The foam is not a prediction of either theory alone. It is a prediction of what must happen when both theories are taken seriously at the same time. It is the universe's way of saying, here is where your understanding runs out. Here is the edge of the map. Here the geometry you have been standing on, quietly, unconsciously all your life, becomes uncertain, at a steady pace. These assumptions are so important that we build our lives on them. We build our lives on assumptions of solidity and continuity. The ground holds. Distance means something. Time flows forward at a steady pace. These assumptions are so deep, we never examine them. They feel like the furniture of reality, fixed and permanent. But physics, in its patient and methodical way, has been quietly discovering that each of these certainties is more conditional than it appears. The ground is curved by mass. Distance is relative to velocity. Time slows in gravitational fields. And now, at the very bottom of the ladder, at the smallest scale where physics can still form a coherent question, even space itself may not be the smooth, passive, featureless stage it has always seemed. The stage, it turns out, may be alive. And to find evidence of that life to catch space in the act of foaming, physicists have had to turn their eyes not inward to the small, but outward to the unimaginably vast. To explosions so powerful they outshine entire galaxies for a fraction of a second. To light that has been traveling since long before the Earth existed, to telescopes that watch the sky not for beauty, but for anomalies, tiny telltale discrepancies in the arrival times of photons that have crossed billions of light years of supposedly smooth, supposedly quiet, supposedly featureless space. And what those telescopes have found and what they have not found turns out to be one of the most revealing chapters in the ongoing story of quantum foam. On May 9th, 2009, a rocket lifted off from the Kourou Space Center in French Guiana, carrying a telescope that would spend the next decade staring at the most violent explosions in the known universe. The telescope was called Fermi, named after Enrico Fermi, the same physicist who had worked alongside Wheeler on the Manhattan Project, the man who built the first nuclear reactor beneath the bleachers of a squash court at the University of Chicago in 1942. The Fermi Gamma Ray Space Telescope was not built to study quantum foam directly. No telescope could do that. But it was built to detect gamma rays, the highest energy form of light arriving from gamma ray bursts, the most luminous events in the observable universe. And embedded quietly in its scientific objectives was a question that connected the largest scales in astronomy to the smallest scales in physics. If space is foamy, at the Planck scale, will the light tell us? But before we can understand what Fermi found and what it means, we need to spend some time with the particles that make the foam possible in the first place. The particles that flicker. The particles that exist and do not exist simultaneously. The particles that are in the most literal sense guests of the vacuum, arriving unannounced, staying briefly and vanishing without a trace. Virtual particles. The word virtual is one of the most misunderstood terms in all of popular science. When people encounter it, they often assume it means imaginary, hypothetical, mathematical abstractions that physicists invented to make their equations work with no real counterpart in the physical world. This is understandable. The word itself invites that interpretation. But it is wrong in a way that matters deeply. Virtual particles are not imaginary. They are not fictions. They are a consequence of the quantum field, the underlying fabric of quantum reality from which all particles emerge. To understand them, we need to understand something about what particles actually are in modern physics. In quantum field theory, particles are not little billiard balls moving through empty space. They are excitations of quantum fields, ripples in fundamental fields that permeate all of space. The electron is a ripple in the electron field. The photon is a ripple in the electromagnetic field. The Higgs boson was famously a ripple in the Higgs field, confirmed at CERN in 2012. Every particle we know corresponds to a field that fills the entire universe. And these fields are never truly at rest. Even in their lowest energy state, the vacuum state, they fluctuate, they oscillate. They produce brief localized disturbances that have the mathematical structure of particles. They carry energy and momentum and interact with other particles, but they do not satisfy the energy-momentum relationship that real observable particles satisfy. They are, in the technical language of quantum field theory, off-shell. They do not live on the mass shell, the mathematical surface in energy-momentum space that defines what a real particle is. This is why they are called virtual, not because they are less real in some philosophical sense, but because they violate the constraint, the on-shell condition that distinguishes a particle you could detect with a particle detector from a transient fluctuation in a quantum field. And because they are off-shell, they are not directly detectable. You cannot build a detector that clicks when a virtual particle passes through it. They exist and vanish too quickly within the time constraints imposed by Heisenberg's energy-time uncertainty relation for any measurement to isolate them individually. But here is what makes virtual particles so extraordinary and so important to the story of quantum foam. Although they cannot be individually detected, their collective effects on real observable particles are measurable. And those effects have been measured with breathtaking precision in some of the most careful experiments in the history of physics. Consider the Lamb shift. In 1947, Willis Lamb and Robert Rutherford measured a tiny discrepancy in the energy levels of the hydrogen atom, a discrepancy that classical quantum mechanics without virtual particles could not explain. The hydrogen atom has an electron orbiting a proton, and quantum mechanics predicts very specific energy levels for that electron. But Lamb and Rutherford found that two energy levels that should, according to the Dirac equation, be exactly equal the two S1/2 and two P1/2 states were in fact slightly different. The difference was tiny, about 1058 megahertz in frequency units, which corresponds to an energy shift of roughly 4 millionths of an electron volt. The explanation provided by Hans Bethe, within a few weeks of Lamb's experimental announcement, was virtual particles. The electron in a hydrogen atom is constantly interacting with virtual photons, fluctuations in the electromagnetic field, that briefly materialize, interact with the electron, and then vanish. These interactions shift the electron's energy levels by a tiny but calculable amount. When physicists computed this shift using quantum electrodynamics, the quantum field theory of light and electrons, they got a number that matched Lamb's measurement to more than 10 significant figures. This is one of the most precise agreements between theory and experiment in all of science. Willis Lamb received the Nobel Prize in Physics in 1955, the same year Wheeler proposed quantum foam. A quiet coincidence of timing that hints at how these ideas were developing in parallel, all pointing toward the same unsettling conclusion. The vacuum is not empty, and its non-emptiness has real measurable consequences. There is another effect worth knowing about here because it connects virtual particles directly to the question of what space is made of in a way that feels almost personal. It is called the anomalous magnetic moment of the electron. Every electron behaves like a tiny magnet. The strength of this magnetism is described by a number called the G factor. Classical physics predicts the G factor should be exactly 2. The Dirac equation, the relativistic quantum mechanical equation for the electron, also predicts it should be exactly 2. But measurements show that it is not exactly 2. It is 2.0, 02, 319, 30, 4, 3, 6, 2, 5, 6, with an uncertainty in the last digit. That tiny deviation from those digits after the decimal point is entirely due to virtual particles. Virtual photons, virtual electron-positron pairs, virtual W and Z bosons, all the fleeting fluctuations of the quantum vacuum contribute measurably to the magnetic behavior of the electron. And when physicists calculate the GE factor using quantum electrodynamics, including contributions from virtual particles to 12 decimal places, they get a number that agrees with experiment to 12 decimal places. 12 decimal places. This is the most precise prediction in the history of science. And every single digit of that precision depends on virtual particles being real, not imaginary, not convenient fictions, but genuine physical participants in the behavior of matter. So, when we say that the quantum vacuum is filled with virtual particles with pairs of particles and antiparticles flickering in and out of existence, we are not speaking metaphorically. We are describing a physical reality confirmed by the most careful measurements humans have ever made. Now here is where virtual particles connect to quantum foam in a way that is both direct and profound. Virtual particle pairs are not uniformly distributed in space. They appear and disappear everywhere, yes, but their behavior is sensitive to the geometry of spacetime. In curved spacetime, the distinction between real and virtual particles becomes blurred in a way that has spectacular consequences. In 1974, Stephen Hawking showed that near the event horizon of a black hole, virtual particle pairs can be separated, one particle falling inward past the horizon, the other escaping to infinity as real radiation. This Hawking radiation, as it came to be called, means that black holes are not perfectly black. They glow faintly with a thermal spectrum determined by their mass, and they slowly evaporate. Hawking radiation has never been directly observed for a black hole of stellar mass. The temperature is so low, it would be completely overwhelmed by the cosmic microwave background. But the theoretical framework that predicts it is the same framework that predicts the Lamb shift and the anomalous magnetic moment. If you trust those predictions and you have 12 decimal places of reason to, then you have strong reason to take Hawking radiation seriously. And Hawking radiation is relevant to quantum foam because it illustrates something essential. Virtual particles respond to space-time geometry. Change the geometry, and you change what the virtual particles do. Make the geometry fluctuate violently as it would in the quantum foam, and the virtual particle behavior at the Planck scale becomes extraordinarily complex. The foam is not just a fluctuation in geometry, it is a fluctuation in the quantum fields that fill that geometry. It is a place where the distinction between real and virtual, between particle and space-time, between matter and geometry, begins to dissolve. This is why quantum gravity, the still missing theory that would reconcile general relativity and quantum mechanics, is sometimes described as a theory not just of space-time, but of space-time and matter together as a unified whole. At the Planck scale, the two cannot be separated. The geometry fluctuates because the quantum fields fluctuate. The quantum fields fluctuate because the geometry fluctuates. They are entangled in a deep, mutual, irreducible way. Think about that for a moment. We tend to imagine space as the container and matter as the contents, the stage and the actors. But at the Planck scale, this distinction may not hold. The stage and the actors may be made of the same stuff, performing the same dance, indistinguishable from each other at the deepest level. Here's a question worth holding quietly. If matter and space-time are ultimately the same thing at the smallest scale, what does that say about the boundary between you and the space you occupy? It is a question without a clean answer, at least not yet. But it is the kind of question that good physics tends to generate, not closing down possibilities, but opening them. Now, back to Fermi. Back to those gamma-ray bursts crossing billions of light-years of space. Because if virtual particles and vacuum fluctuations distort the geometry of space-time at the Planck scale, and if that distortion affects the propagation of light, then the most energetic photons in the universe arriving from the most distant explosions in the cosmos should carry a faint but detectable signature of that distortion. The logic is elegant in its simplicity. A gamma-ray burst releases an enormous spectrum of photons, from relatively low-energy gamma rays to very high-energy gamma rays, all at essentially the same moment. They begin their journey together, side by side, racing across the universe at the speed of light. If space-time is perfectly smooth, they should arrive together high-energy and low-energy photons reaching Earth at precisely the same time after billions of years of travel. But if space-time is foamy, if high-energy photons interact differently with the granular texture of Planck-scale space than low-energy photons do, then the arrival times should differ by a tiny amount, an amount that would be completely undetectable over short distances. But that might accumulate over billions of light-years into something measurable. In 2009, the Fermi telescope observed a gamma-ray burst designated GRB 90510, located approximately 7 billion light-years from Earth. The burst released photons across a wide range of energies, and Fermi measured their arrival times with extraordinary precision. One photon in particular, with an energy of about 31 billion electron volts, making it the highest energy photon ever associated with a gamma-ray burst at that time, arrived just 9/10 of a second after the lower energy photons in the burst. 9/10 of a second after 7 billion years of travel. Now, was this a signature of quantum foam? Was the high-energy photon slowed by its interactions with the granular texture of Planck-scale space-time? The answer, when physicists analyzed it carefully, was both illuminating and humbling, and it points toward a truth about quantum foam that is more subtle and in some ways more interesting than a simple yes or no. That analysis and what it reveals about the models of quantum foam that physicists have been building carries us directly into one of the most active frontiers in all of modern physics. A frontier where the largest instruments ever built are being turned toward questions so small that no instrument could ever directly resolve them, and where the answers, whatever they turn out to be, will tell us something fundamental about the nature of the space we have been drifting through all our lives. The Fermi telescope's measurement of GRB 090510, that 9/10 of a second delay between a high-energy photon and its lower energy companions after 7 billion years of travel, was not, as it turned out, a confirmation of quantum foam. It was something more interesting than that. It was a constraint, a boundary, a line drawn in the sand of physics that said, if quantum foam exists, it cannot be quite the way some people imagined it. To understand why this matters, why a null result, a non-detection, can be as scientifically valuable as a positive discovery, we need to spend some time with the question of what it actually means to look for something that may be by its very nature beyond the reach of direct observation. This is one of the deepest methodological challenges in all of modern physics, and it is a challenge that reveals something important, not just about quantum foam, but about the nature of scientific knowledge itself. Let's begin with the Fermi result and work outward from there. When physicists analyze the arrival time difference of that high-energy photon from GRB 090510, they did something careful and precise. They took the observed delay 9/10 of a second and asked, could this be explained by quantum foam? Specifically, could it be explained by the simplest, most naive model of quantum foam, in which the effect on photon propagation is proportional to the photon's energy and the distance traveled? The answer was no, and the reason was stark and quantitative. For the delay to be caused by quantum foam interacting linearly with photon energy, the scale of the foam, the characteristic length at which the granularity of space becomes significant, would need to be larger than the Planck length. Specifically, the Fermi result placed an upper limit on the quantum gravity scale, the energy scale at which space-time granularity would become apparent, that was actually higher than the Planck energy itself. In other words, if quantum foam causes linear dispersion in photon propagation, then space-time must be smooth at scales even smaller than the Planck length, which means either quantum foam doesn't cause this kind of dispersion, or the Planck length is not where the foam lives, or the simple linear model of how foam affects light is wrong. This is a genuine scientific result. It rules out an entire class of quantum gravity models, specifically the models that predict a linear relationship between photon energy and propagation speed modification. It does not rule out quantum foam itself. It rules out a particular way that quantum foam might manifest. The distinction matters enormously, and it illustrates a principle that is worth understanding clearly. In science, the absence of evidence for a specific prediction is not the same as evidence against the underlying idea. It is evidence against that specific model of the underlying idea. Think of it this way. Imagine you are trying to determine whether a distant mountain exists, but you can only infer its presence from the shadows it casts at different times of day. If you look for a shadow at noon and find none, you have not proven the mountain doesn't exist. You have proven that either the mountain is too small to cast a detectable shadow at noon, or it is oriented in a way that hides the shadow, or your model of shadow casting was wrong. You continue looking. You look at different times in different ways with different instruments. This is precisely what physicists have been doing with quantum foam. The Fermi result closed one door. Other doors remain open, and some of those doors lead to experiments and observations that are currently underway, producing results that will shape our understanding of space-time for decades to come. One of the most intriguing of these is the holographic noise experiment conducted at Fermilab, the particle physics laboratory outside Chicago, that has been since its founding in 1967 one of the great centers of experimental physics in the world. In 2010, Craig Hogan, a physicist at Fermilab, proposed a specific model of quantum foam based on holographic principles. The idea borrowed from black hole thermodynamics and string theory that three-dimensional space might be in some sense encoded on a two-dimensional surface, the way a hologram encodes a three-dimensional image on a flat photographic plate. In Huygens' holographic noise model, the quantum uncertainty of space-time at the Planck scale would manifest as a kind of correlated jitter, a noise in the positions of objects separated by macroscopic distances, not random but structured. Not tiny effects that only matter at the Planck scale, but effects that, due to the holographic encoding of information, might be detectable at much larger scales using extremely precise interferometers. Huygens and his team built an instrument called the holometer-2 interferometers, placed side by side, each measuring the relative positions of mirrors to extraordinary precision, looking for correlated fluctuations in their readings. That would be the signature of holographic noise. The holometer ran for over a year, collecting data with a sensitivity that probed length scales far below any previous macroscopic measurement. The result, published in 2016, was again a non-detection. The holometer found no evidence of correlated holographic noise at the level Huygens' model predicted. This ruled out that specific version of the holographic foam model. Huygens himself acknowledged the result and began refining his theoretical framework. But here is what is striking about both the Fermi result and the holometer result. They are not failures. They are achievements. Each one has done something that no previous experiment could do. It has probed the Planck scale, however indirectly, with sufficient precision to rule out specific models. And ruling out specific models is how physics makes progress. Every door that closes points more clearly toward which doors remain open. There is a common misconception in popular science that experiments are either successes they confirm the theory or failures they don't. This binary view misses the actual texture of scientific progress. In reality, a well-designed experiment that returns a null result, that finds nothing where a specific model predicted something, is often more valuable than a sloppy experiment that seems to confirm a vague prediction. Precision null results are the sharpest tools in the physicist's toolkit. They carve away the space of possibilities, concentrating attention on what remains. Consider what happened with the Michelson-Morley experiment in 1887. Albert Michelson and Edward Morley designed an extraordinarily precise interferometer to detect the motion of the Earth through the luminiferous ether, the hypothetical medium through which light was supposed to propagate, analogous to the way sound propagates through air. They found nothing. No ether wind, no motion relative to the ether at all. For a decade, this null result was an embarrassment, a mystery without resolution. Then Einstein in 1905 realized that the null result was not a failure of the experiment. It was a precise description of reality. There was no ether. Light did not need a medium. The speed of light was the same in all reference frames. The null result of Michelson-Morley was not a dead end. It was the foundation of special relativity. The null results from Fermi and the holometer may be pointing towards something similarly fundamental. We do not yet know what, but the pattern is suggestive. The simplest, most naive models of quantum foam, the ones that predict large, easy-to-detect effects, are being ruled out one by one. What is emerging is a picture in which, if quantum foam exists, it is subtler than we first imagined, more hidden, more elusive, perhaps operating through mechanisms that are not yet part of our theoretical vocabulary. And this leads to one of the most profound challenges in the search for quantum foam, which is not experimental, but theoretical. We do not yet have a complete self-consistent theory of quantum gravity that makes sharp, unambiguous predictions about what quantum foam should look like. We have hints. We have models. We have framework string theory loop, quantum gravity, causal set theory, asymptotic safety, each of which paints a slightly different picture of Planck-scale physics. But none of them has yet been formulated precisely enough or tested rigorously enough to serve as the definitive guide that experiments need to confirm or falsify. This is unusual in physics. Normally, experimental searches are guided by well-defined theoretical predictions. You calculate what you expect. You design an experiment to test it, and the experiment returns a result that either confirms or refutes the calculation. The search for quantum foam is more like exploring a coastline in fog. The coast is there, approximately where it must be. But the fog is thick enough that you are feeling your way forward with instruments rather than following a clear map. There is, however, one approach to finding evidence of quantum foam that is both theoretically motivated and observationally accessible, and it does not involve gamma-ray bursts or interferometers. It involves the faint cold afterglow of the Big Bang itself. The cosmic microwave background, the CMB, is a snapshot of the universe when it was approximately 380,000 years old, the moment when the hot plasma of the early universe cooled enough for atoms to form and light to travel freely for the first time. That ancient light stretched by the expansion of the universe to microwave wavelengths fills the sky in every direction with a nearly uniform glow at a temperature of approximately 2.725 Kelvin, just a few degrees above absolute zero. But the CMB is not perfectly uniform. It has tiny temperature fluctuations variations of about 1 part in 100,000 that represent the seeds of all the structure in the universe, the galaxies, the galaxy clusters. The great walls and voids of the cosmic web, all of it grew from these tiny fluctuations in the early universe. And the pattern of these fluctuations carries information about the physics that generated them. Most cosmologists believe these fluctuations were generated by a process called cosmic inflation, a period of extraordinarily rapid expansion in the first tiny fraction of a second after the Big Bang, during which the universe expanded by a factor of at least 10 to the 26th power in an interval estimated at around 10 to the negative 32 seconds. During inflation, quantum fluctuations in the inflaton field, the field driving the expansion, were stretched to cosmic scales, becoming the seeds of structure we observe in the CMB today. But inflation happened at energy scales that may have been close to the Planck scale. If quantum foam is real, if space-time was frothing at Planck energies, then the fluctuations produced during inflation may carry a faint imprint of that foaming, a specific signature in the CMB power spectrum, or in the pattern of primordial gravitational waves that would be the fingerprint of Planck-scale physics written across the sky in ancient light. Current and future CMB experiments, including the BICEP/Keck array at the South Pole and the proposed CMB-S4 experiment, are searching precisely for this signature. They are looking for the faint curl of polarization in the CMB called B modes, which would indicate the presence of primordial gravitational waves from the inflationary era. If detected with sufficient precision, these B modes could carry information about the energy scale of inflation and potentially about the quantum nature of spacetime at that scale. This is perhaps the most extraordinary thing about the search for quantum foam. The evidence, if it exists, may not be found at the smallest scales with the most powerful microscopes. It may be found at the largest scales written across the entire sky in the polarization of the oldest light in the universe. The cosmos itself may be the detector. The Big Bang may have been the experiment. Sit with that for a moment. The idea that the answer to a question about the texture of space at 10 to the negative 35 meters might be encoded in the pattern of temperature fluctuations stretched across billions of light years. This is the kind of connection that makes physics feel at its best, not just like a collection of facts, but like a revelation. A slow, patient, collaborative revelation built by generations of scientists who trusted the mathematics enough to follow it wherever it led, even when it led somewhere no instrument could yet reach. And yet, for all the ingenuity of these observational strategies, gamma-ray bursts, interferometers, the cosmic microwave background, there is a deeper question lurking beneath all of them. A question not about how to detect quantum foam, but about what quantum foam actually is, what it is made of, what the correct theory of it looks like. Whether the foam is a feature of space-time itself or an emergent property of something more fundamental, something that space-time is made of, the way water is made of molecules, the way molecules are made of atoms, the way atoms are made of quarks and electrons and the quantum fields that give them being. That question, the question of what space-time is made of at the deepest level, is where the two great competing theories of quantum gravity diverge most dramatically. And understanding where they agree, where they disagree, and what experiments might one day distinguish between them is the next step in this quiet, careful journey into the smallest things. Two theories, two visions, two fundamentally different answers to the same ancient question, what is space made of, at its deepest level? And between them, one of the most fascinating intellectual contests in the history of science. It is a contest that has been running for nearly half a century. It has consumed the careers of some of the most gifted theoretical physicists alive. It has generated thousands of papers, dozens of books, and no small amount of genuine animosity between its participants. And as of today, neither side has won, neither side has lost. The universe as yet has not declared a verdict. But the contest itself, the ideas in conflict, the assumptions being challenged, the different pictures of reality being painted, is one of the most beautiful things in all of modern physics, and understanding it changes the way you see the space around you tonight. Let's begin with string theory, because it came first, and because its story begins in an unexpected place, not with gravity, not with space-time, but with the strong nuclear force. In 1968, a young Italian physicist named Gabriele Veneziano was working at CERN, trying to understand the mathematical patterns in the scattering of strongly interacting particles, hadrons, the family of particles that includes protons and neutrons. He found a formula now called the Veneziano amplitude that described the scattering data with surprising accuracy. What was remarkable was that this formula had been written down a century earlier by the Swiss mathematician Leonhard Euler in a completely different context. It was called the Euler beta function, and it had nothing originally to do with physics at all. 2 years later, in 1970, physicists Yoichiro Nambu Holger Nielsen and Leonard Susskind independently realized what Veneziano's formula was actually describing. It was the behavior of a tiny one-dimensional vibrating object, a string. If you replace the point particles of conventional physics with tiny strings, and if you allowed those strings to vibrate at different frequencies, the Veneziano amplitude emerged naturally from the mathematics. The different vibrational modes of the string corresponded to different particles, the way different vibrational modes of a guitar string produce different musical notes. This was intriguing, but initially puzzling. The strong force already had a perfectly good description, quantum chromodynamics. The theory of quarks and gluons in string theory, as originally formulated, had problems. It required 26 space-time dimensions to be mathematically consistent. It predicted a particle with imaginary mass, a tachyon, that seemed to indicate an instability in the theory. It appeared to be a dead end. Then, in 1974, two physicists, Joel Shirk in Paris and John Schwartz at Caltech, made a suggestion that would transform string theory from a failed model of the strong force into a candidate for the theory of everything. They noticed that among the vibrational modes of the string, there was always one that corresponded to a massless particle of spin 2. And a massless spin 2 particle is precisely what a quantum theory of gravity requires. It is the graviton, the hypothetical carrier of the gravitational force. String theory had not been looking for gravity. Gravity had found it. This was the moment string theory became a theory of quantum gravity. The graviton emerged naturally without being put in by hand. Gravity was not an add-on. It was an inevitable consequence of the mathematics of vibrating strings. And because the other forces of nature, electromagnetism, the weak force, the strong force, also emerged from different vibrational modes of the string, there was a genuine possibility that string theory was a unified description of all forces and all matter, a single framework from which everything else could be derived. Through the 1980s, string theory developed rapidly. The tachyon problem was resolved by incorporating supersymmetry, a theoretical symmetry between matter particles and force carriers, producing what became known as superstring theory. The requirement of 26 dimensions was reduced to 10, and in 1985, physicists discovered that there were actually 5 different versions of consistent superstring theory, 5 different mathematical frameworks, each self-consistent, each appearing to describe a different universe. This proliferation was concerning. If there were 5 versions, which one described our universe? The question was not resolved until 1995, when Edward Witten, widely regarded as the most mathematically gifted theoretical physicist of his generation, proposed that all 5 versions were actually different limiting cases of a single deeper theory he called M-theory existing in 11 dimensions. The 5 string theories were like 5 different shadows of the same higher dimensional object, each shadow looking different depending on the angle from which you viewed it. M-theory was profound and beautiful. It was also and remains only partially understood. Its full mathematical formulation has never been written down. Its prediction specifically which of the vast landscape of possible string theory vacua corresponds to our universe have not been determined. The string theory landscape as it is known contains an estimated 10 to the 500th power possible universes, each with different physical constants, different particle masses, different laws of nature. Finding our universe in that landscape is, to put it gently, a work in progress. Now here's the contrast. While string theorists were building their elaborate mathematical cathedral of vibrating strings and extra dimensions, another group of physicists, smaller in number, but no less determined, was taking a completely different approach. They were not trying to unify all forces. They were not looking for a theory of everything. They were focused on a single specific problem. How do you quantize gravity directly? How do you apply the standard procedures of quantum mechanics to the geometric degrees of freedom of general relativity to the metric? The mathematical object that describes the curvature of space-time without assuming a fixed background. The key figure in this program was Abhay Ashtekar, an Indian-American physicist who in 1986 found a new way to reformulate general relativity that made it look much more like the other quantum field theories physicists already knew how to quantize. In Ashtekar's formulation, the variables describing space-time geometry were not the metric itself, but a set of connection variables, mathematical objects that described how vectors rotated as they were transported through curved space-time. This reformulation, while technically demanding, opened a door that had previously been closed. Building on Ashtekar's work, Carlo Rovelli and Lee Smolin, working independently and then together through the late 1980s and 1990s, developed what became known as loop quantum gravity. When they applied the quantization procedure to Ashtekar's variables, the results were striking. The quantum states of the gravitational field were not smooth fields defined on a continuous background. They were discrete structures, networks of interconnected loops, later generalized to what Rovelli and Smolin called spin networks. A spin network is a graph, a collection of nodes connected by edges where each edge carries a label representing a quantum number of area, and each node carries a label representing a quantum number of volume. The geometry of space in loop quantum gravity is not a smooth continuum. It is a quantum lattice. Space is made of discrete chunks, quanta of volume connected by quanta of area. There is a smallest possible volume of the order of the Planck volume. There is a smallest possible area of the order of the Planck area. Below these scales, the concepts of distance and geometry simply do not apply. The foam in loop quantum gravity is not a fluctuation on a smooth background. It is the quantum superposition of different spin network configurations. Space is foamy because the quantum state of geometry is a superposition of many different discrete networks, the way the quantum state of an electron is a superposition of many different positions. The apparent smoothness of space at ordinary scales is the classical limit, the large-scale average of this underlying quantum discreteness, the way the apparent smoothness of water is the large-scale average of the discrete molecular structure beneath. This is a genuinely different picture from string theory. In string theory, space-time remains smooth. The strings vibrate in a background space-time, and the foam emerges from the dynamics of strings at the Planck scale. In loop quantum gravity, there is no background space-time. Space-time itself is the quantum object. The foam is not something that happens in space. The foam is what space is. Here is a question worth pausing on. Which of these pictures feels more natural to you, space as a smooth stage on which quantum strings dance, or space itself as a quantum object, grainy and discrete at the smallest scale? There is no right answer here. Both are supported by serious mathematics. Both have serious physicists behind them. And the fact that two such different pictures can both be self-consistent is itself telling us something about how much we still don't know. The tension between string theory and loop quantum gravity is sometimes portrayed in popular science as a personal rivalry, a battle between camps fueled by academic politics and institutional allegiances. And it would be dishonest to pretend that human dynamics play no role. String theory has historically attracted more funding, more students, more institutional prestige, in part because of its ambition and in part because of the mathematical richness of the tools it uses. Loop quantum gravity has sometimes been dismissed by string theorists as insufficiently ambitious, lacking the unifying vision that string theory provides. Loop quantum gravity practitioners have sometimes criticized string theory for its lack of testable predictions and its apparent disconnection from experimental physics. But beneath the human drama, there is a genuine and important scientific disagreement. And the most honest assessment is this: both theories have made real mathematical progress. Both have taught us something true and important about the structure of quantum space-time. String theory has given us the holographic principle, the ADS/CFT correspondence, and deep insights into black hole thermodynamics. Loop quantum gravity has given us a rigorous framework for discrete quantum geometry and specific predictions about the quantum nature of area and volume. What neither has given us yet is a clear, unambiguous, experimentally confirmed prediction that distinguishes it from the other or from all other possible theories of quantum gravity. This is the frontier. This is where the work remains. And there is a third approach worth mentioning, quieter than the others, but in some ways the most elegant. It is called causal set theory, developed primarily by Raphael Sorkin and his collaborators since the 1980s. Causal set theory begins with a simple, almost minimalist assumption. Space-time is fundamentally discrete, composed of indivisible events, points in space-time connected only by causal relations. The relations of before and after cause and effect. The geometry of space-time distances, volumes, curvature, all emerge from the pattern of these causal connections. Nothing else is assumed. No extra dimensions, no strings, no fields on a background. Just events and their causal order. The extraordinary thing about causal set theory is that it made a specific quantitative prediction years before the observation. It predicted about the value of the cosmological constant, the energy density of empty space that drives the accelerating expansion of the universe. In 1990, Sorkin predicted on the basis of causal set arguments that the cosmological constant should be small but non-zero, of order 1, over the square of the wide of the universe in Planck units. In 1998, astronomers measuring the brightness of distant supernovae discovered that the expansion of the universe was indeed accelerating, driven by a cosmological constant that was small but non-zero, of precisely the order Sorkin had predicted. This is not widely known. It does not receive the attention it deserves. But it is a genuine instance of a quantum gravity theory making a prediction that was later confirmed by observation, the kind of thing that string theory and loop quantum gravity have not yet managed. Causal set theory remains a minority view, less mathematically developed than its competitors. But its cosmological constant prediction stands as a quiet reminder that sometimes the most important ideas are the ones that make the fewest assumptions. What all three approaches share, string theory loop, quantum gravity, causal set theory, is a conviction that the smooth space-time of general relativity is not the final word. That at the Planck scale, something more fundamental takes over, something discrete or stringy or causally ordered, something that produces the foam Wheeler imagined, or something even stranger than foam, a structure for which we do not yet have a name or a geometry. And perhaps the most important lesson from this war of ideas is not which theory will ultimately win. It is what the contest itself reveals about the practice of science at its frontier. Science at its best is not a march toward a single predetermined answer. It is a competition of ideas constrained by mathematics, an experiment in which wrong answers are gradually eliminated and right answers slowly emerge, sometimes from unexpected directions, sometimes through null results, sometimes through a single elegant prediction that no one expected to be confirmed. The war between string theory and loop quantum gravity has not yet produced a winner, but it has already changed the landscape of physics permanently. It has established that space-time at the Planck scale is almost certainly not what it appears to be at everyday scales. It has shown that the question of quantum foam is not just a philosophical curiosity, but a central problem in fundamental physics with implications that reach from the structure of black holes to the origin of the universe to the ultimate nature of matter and energy. And it has opened a door still ajar, still allowing only a sliver of light onto a view of reality that is deeper, stranger, and more wonderful than anything Newton or Einstein could have imagined on their most expansive days. What lies beyond that door is where our journey goes next. Beyond that door, it turns out, is a mirror, not a mirror that reflects your face, a mirror that reflects your assumptions about what is real, about what is solid, about what it means to exist in a universe whose deepest foundations may be nothing, like the stable, continuous, well-behaved space you have always taken for granted. The question of whether space is foamy is not just a question for physicists with equations and telescopes. It is a question that reaches into philosophy, into neuroscience, into the most ordinary moments of everyday life in ways that are quiet but profound. Because if quantum foam is real, if the smoothness of space is an illusion, an emergent property of something far more chaotic at the smallest scales, then we are living on the surface of a deep complexity we cannot see, cannot feel, and cannot directly measure. And that situation is not as strange or as new as it might seem. In fact, we have been living in exactly this situation all along, just at different scales. Consider what the neuroscience of perception has taught us over the past several decades. The world you experience right now, the warmth of wherever you are, resting the quality of the light, the sense of continuous space stretching in all directions around you is not a direct recording of reality. It is a construction. Your brain receives fragmented, incomplete, noisy signals from your senses. Photons striking the retina pressure waves, vibrating the eardrum, chemical signals binding to receptors. And from these discrete, discontinuous inputs, it builds a seamless, continuous, richly detailed experience of a three-dimensional world. This construction is extraordinarily good. Evolution has had hundreds of millions of years to refine it, and the result is a perceptual system of remarkable accuracy and speed. But it is a construction nonetheless. The continuity you perceive, the sense that the floor beneath you is solid and smooth, that the space between objects is a featureless void, is something your brain assembles, not something it passively records. The neuroscientist Carl Friston at University College London has developed an influential framework called predictive processing, or active inference, which proposes that the brain is fundamentally a prediction machine. Rather than passively receiving sensory data and constructing a picture of the world from scratch with each moment, the brain maintains a continuous internal model of reality, a generative model, and constantly updates it by comparing its predictions to incoming sensory signals. What we experience as perception is not the raw sensory data itself, but the brain's best prediction of what is causing that data. The world we see is the world our brains predict. This framework has striking resonance with what quantum gravity is telling us about space-time. The smooth, continuous space of our experience is, in some deep sense, a prediction and emergent order imposed on something that is at its foundations neither smooth nor continuous. We cannot experience the Planck scale directly. Our sensory apparatus operates at scales many orders of magnitude larger, but the experience of smooth space that our perceptual system generates is in its structure analogous to what physicists call the classical limit, the large-scale average of quantum behavior that emerges when you are far enough from the Planck scale that the discreteness and the foam become invisible. There is something quietly remarkable about this parallel. The brain builds a smooth, continuous world from discrete, noisy signals. The universe, it seems, builds a smooth, continuous space-time from discrete, foamy quantum geometry. The mechanism is different, the scale is incomparably smaller, and one should be careful not to overstate the analogy. But the structural similarity emergence of apparent continuity from underlying discreteness is not coincidental. It reflects something deep about how complex systems behave at different scales. Now, let us take this idea somewhere more concrete because there is a specific and fascinating implication of quantum foam that connects directly to something you may have encountered without recognizing it, the concept of emergent space-time. One of the most striking developments in theoretical physics over the past 2 decades is the growing suspicion shared by physicists across several different research programs that space-time is not fundamental, that it does not belong in the list of basic ingredients from which the universe is built, the way we might list quarks and electrons and the forces between them. Instead, space-time, including its smoothness, its dimensionality, its causal structure, may emerge from something more fundamental, something that is not itself spatial or temporal. The clearest hint of this comes from the ADS/CFT correspondence discovered by Juan Maldacena in 1997. This is one of the most celebrated results in theoretical physics in the past 30 years, and it is at its core a statement about the relationship between space-time and information. ADS/CFT anti-de Sitter/conformal field. Theory correspondence establishes a precise mathematical equivalence between 2 very different kinds of theories. On one side is a theory of gravity in a particular kind of curved space-time, anti-de Sitter space, a space-time with a specific constant negative curvature. On the other side is a quantum field theory, specifically a conformal field theory, defined not in that space-time, but on its boundary a surface with one fewer dimension. The 2 theories are dual. They describe the same physics from different perspectives. Every event, every process, every particle interaction in the bulk of the anti-de Sitter space has an exact counterpart in the boundary field theory and vice versa. What this means in its most striking interpretation is that a theory of gravity in 3 spatial dimensions is exactly equivalent to a theory without gravity in 2 spatial dimensions. The 3rd dimension of space and the gravitational dynamics within it emerges from the quantum entanglement structure of the 2-dimensional boundary theory. Space itself in this picture is not fundamental, it is emergent. It is encoded in the pattern of quantum correlations on a lower dimensional surface, the way the image in a hologram is encoded in the interference pattern on a flat photographic plate. This is the holographic principle, not the speculative version proposed by Craig Hogan that we discussed in the context of the holometer experiment, but the rigorous, mathematically precise version established by Maldacena's correspondence. And its implications for quantum foam are profound. If space-time is emergent, if the 3-dimensional space we inhabit is encoded in quantum information on a 2-dimensional boundary, then the foam is not a fluctuation in the fabric of a pre-existing space. The foam is a fluctuation in the quantum information that generates space. The granularity is not a property of space. It is a property of the information from which space is built. This is a conceptual shift so large that it is difficult to fully absorb. We are accustomed to thinking of information as something that exists in space data, stored in a physical medium, patterns encoded in matter that occupies a specific location. But the holographic principle inverts this completely. Space exists in information. Location is a derived concept, not a primary one. The smooth, continuous three-dimensional space you are resting in tonight is, if this picture is correct, a kind of elaborate holographic projection, a macroscopic pattern that emerges from microscopic quantum correlations on a surface you cannot see and cannot point to. Here is a question to hold gently without trying to resolve it. If the space around you is emergent, if it is built from information rather than existing independently of information, what does that say about the nature of physical reality? Not as a philosophical puzzle to be solved, but as a fact to be wondered at. The universe is stranger than it looks. The floor is less solid than it feels. And the strangeness is not a flaw. It is in some deep sense the most interesting thing about the place we live. Now, let us come down from these heights for a moment and look at something more concrete, a real-world implication of the quantum vacuum and vacuum fluctuations that affects technology we actually use right now in ways that most people never think about. Quantum vacuum fluctuations. The same fluctuations that Wheeler argued would distort spacetime at the Planck scale have measurable effects on the behavior of electronic devices at the nanoscale. As transistors and modern computer chips have shrunk to dimensions of just a few nanometers, approaching the scale at which quantum effects dominate classical behavior, engineers have had to grapple directly with quantum vacuum effects. Vacuum fluctuations contribute to a phenomenon called quantum noise, which sets a fundamental limit on how precisely electronic signals can be measured and how reliably transistors can switch between on and off states at the nanoscale. This is not an engineering inconvenience. It is a reminder written in the language of semiconductor physics that the quantum vacuum is real and consequential at scales far larger than the Planck scale. The same underlying physics quantum field fluctuations in the vacuum that Wheeler imagined frothing spacetime at 10 to the negative 35 meters is also setting the noise floor for the chips in your phone and your computer. The scale is different. The principle is the same. And there is a branch of physics and engineering, quantum metrology, devoted precisely to exploiting vacuum fluctuations rather than fighting them. In quantum-enhanced measurement, physicists use a technique called squeezed light, a quantum state of light in which the uncertainty in one property, such as phase, is reduced below the vacuum level at the expense of increased uncertainty in another property, such as amplitude, in accordance with the Heisenberg uncertainty principle. Squeezed light is currently being used at the advanced LIGO gravitational wave detectors to improve their sensitivity beyond what would be possible with classical light alone. The gravitational waves that LIGO detected, ripples in space-time from colliding black holes and neutron stars, were found in part by harnessing the quantum vacuum in a controlled and sophisticated way. Think about that chain of connection. Wheeler imagines that space-time foams at the Planck scale because the quantum vacuum fluctuates. Decades later, physicists build instruments sensitive enough to detect ripples in space-time itself and make those instruments work better by manipulating the quantum vacuum. The foam and the detector are made of the same physics. The hunter uses the same substance as the quarry. There is something almost poetic about this in the most rigorous sense of the word. Poetic, not decorative, but structurally resonant. The quantum vacuum connects the smallest scales we can imagine to the largest phenomena we can observe. It connects the theoretical abstractions of Planck scale physics to the practical realities of semiconductor engineering and gravitational wave detection. It connects Wheeler's 1955 paper to LIGO's 2015 detection with a chain of physical reasoning that is unbroken and at each link experimentally verified. And perhaps the most human lesson in all of this, the lesson that reaches beyond physics into something more universal, is about the relationship between what we can see and what is real. Throughout history, the things that have turned out to matter most have often been the things that were for a long time invisible: germs, atoms, electromagnetic fields, dark energy, the quantum vacuum, the foam. We are pattern-recognizing creatures living at a particular scale, equipped with senses tuned to the middle range of the universe's size spectrum, too large to feel the quantum, directly too small to see the cosmic, directly navigating a narrow band of experience that we have for most of history, mistaken for the whole. Science at its best is the systematic effort to extend our reach beyond that narrow band, to see the very large and the very small, the very fast and the very slow, the very hot and the very cold, and to find in those extended views the deeper patterns that our unaided senses cannot reach. Quantum foam is one of those patterns, unseen, perhaps unseeable directly, but present in the mathematics, in the equations, in the experimental constraints, in the theoretical frameworks that have been tested and refined and extended over 70 years of careful work. Present the way a deep ocean current is present beneath a calm surface, invisible from above, but shaping everything that floats. You are resting right now on the surface of that depth. The space beneath you and around you and between the atoms of your body is if the best current thinking in physics is anywhere near correct, not the featureless void it seems. It is layered, it is structured, it is at the very bottom of the ladder, doing something extraordinary that no language developed for ordinary experience is quite equipped to describe. And yet, we try, with mathematics, with metaphor, with the quiet persistence of people who believe that understanding the universe is worth the effort, even when the universe declines to make itself easy. The extraordinary thing is how far that persistence has brought us, from Newton's absolute featureless space to Einstein's flexible dynamic space-time, from the quantum vacuum of Heisenberg and Casimir to the virtual particles confirmed by 12 decimal places of precision, from Wheeler's 1955 speculation to the Fermi telescope, the holometer, the cosmic microwave background, and the ongoing unfinished magnificent effort to find the theory that sits beneath them all. We have not yet found it, but we know with more certainty than at any previous moment in history what we are looking for. And that knowledge, the knowledge of where the question lives, of what form the answer must take, of which experiments might one day reveal, it is itself a kind of light in the darkness, faint perhaps, but real, and pointed however uncertainly in the right direction. That direction leads us finally to the most intimate question of all, not what space is made of at the Planck scale, not which theory of quantum gravity is correct, but what it means for you resting here tonight in the quiet space between waking and sleeping to live in a universe whose foundations are this deep, this strange, and this beautifully unfinished. What does it mean to live in a universe whose foundations are unfinished? Not unfinished in the way a house is unfinished, waiting for someone to lay the last floorboard, hang the last door. Unfinished in a deeper sense. Unfinished the way a question is unfinished, when it has been asked with perfect clarity, but answered only in fragments, each fragment beautiful, each fragment true, and none of them yet assembled into a complete picture that anyone fully understands. This is where we find ourselves tonight, at the edge of what is known, looking out over what is not. And perhaps the most honest and most extraordinary thing about this moment in the history of physics is that the scientists working at this edge, the people spending their careers on quantum gravity, on the structure of space-time, on the nature of the foam, are not frustrated by the incompleteness. Most of them, if you ask them, will tell you that the incompleteness is the best part, that working at the frontier of the unknown is the closest thing to a secular form of wonder that the modern world offers, that waking up each morning to a problem that has not been solved, that may not be solved in their lifetime, is not a burden. It is a privilege. Carlo Rovelli, the Italian physicist who helped build loop quantum gravity, and who has written about the philosophy of physics with unusual clarity and grace, put it this way in his book, 7 Brief Lessons on Physics, a book that sold over 1 million copies in Italy alone before being translated into 40 languages, which suggests that the hunger for this kind of wonder is not limited to physicists. Ravelli wrote that the beauty of physics lies not in the answers it has found, but in the questions it has learned to ask, that the greatest achievement of science is not certainty, but the precise identification of what we do not yet know. This is a hard idea to hold in a culture that prizes answers. We are surrounded by information, by confident assertions, by headlines that declare discoveries and breakthroughs, and paradigm shifts on an almost daily basis. Against this background noise of certainty, the quiet admission that the most fundamental question in physics, what is space-time made of, remains genuinely deeply open is almost countercultural. It asks us to be comfortable with not knowing, to find something valuable in the unresolved. But here is what the history of physics teaches us about this kind of open question. The questions that stay open the longest, the ones that resist resolution for decades or centuries, are almost always the questions that, when finally answered, change everything. Not just physics, everything. Consider what happened when Newton answered the question of what governs the motion of planets and falling apples. The answer, universal gravitation described by a single mathematical law, did not just explain the motion of the moon. It gave humanity the conceptual tools to eventually build satellites to navigate by GPS to understand the large-scale structure of the universe. The answer to one deep question opened 1,000 doors that Newton himself could never have imagined. Consider what happened when Maxwell answered the question of what light is. His answer, that light is an electromagnetic wave described by 4 elegant equations, did not just explain optics. It predicted radio waves, which led to wireless communication, which led to the entire infrastructure of the modern connected world. Maxwell's equations, written in the 1860s, are running in every Wi-Fi router in every cell tower on Earth right now, as you listen to these words. Consider what happened when Einstein answered the question of what gravity is. His answer that gravity is the curvature of space-time did not just explain the precession of Mercury's orbit. It predicted the existence of black holes, gravitational waves, and the expanding universe. It gave us the GPS satellites, whose atomic clocks must correct for relativistic time dilation to give accurate positions. It gave us the image of M87's black hole photographed by the Event Horizon Telescope. In 2019, a photograph of a shadow cast by an object so massive that not even light can escape it, exactly as Einstein's equations predicted a century earlier. Each of these answers to deep questions changed the world in ways the questioners could not foresee. And the question of quantum foam, of what space-time is made of at the Planck scale, of how gravity and quantum mechanics fit together, is deeper than any of them. It sits beneath all of them. It is the question that the answers to those earlier questions were pointing toward all along. When it is answered, and it will be answered by someone someday, perhaps in a decade, and perhaps in a century, the answer will not merely add a chapter to the physics textbooks. It will rewrite the first chapter, the chapter about what space is, what time is, what it means for anything to exist anywhere at any moment. And from that rewriting, applications and implications will flow that we cannot currently imagine the way Maxwell could not have imagined Wi-Fi, the way Newton could not have imagined GPS. This is not speculation. This is the pattern of physics across 4 centuries of history. Deep questions, when answered, are generative beyond all prediction. So, what does it mean practically and personally to live now at this specific moment in the history of science, when the question is open, but the tools to answer it are being built, when the experiments are running and the theories are being refined and the answer is somewhere in the future, waiting? It means something specific and something important. It means that the universe is right now more mysterious than it has ever been, not less. We know more than any previous generation of humans. We have mapped the genome, detected gravitational waves, photographed black holes, landed rovers on Mars, built machines that can process information at speeds incomprehensible to unaided human cognition. And yet, the more we know, the clearer the shape of what we do not know becomes. The deeper the questions get, the more precisely the mystery is defined. In 1900, the British physicist Lord Kelvin, one of the giants of 19th century science, reportedly told an audience at the British Association for the Advancement of Science that physics was essentially complete, that there was nothing fundamentally new to discover, that the remaining work was merely to measure known quantities to greater precision. He pointed to just two small clouds on the horizon of physics, two unexplained phenomena that would, he apparently believed, soon be cleared up by minor adjustments to existing theory. Those two small clouds were the failure of the Michelson-Morley experiment to detect the ether and the problem of blackbody radiation. The first cloud became special relativity. The second became quantum mechanics. Together, they did not clear the sky. They remade it entirely. We should be humble about what we think we know, not paralyzed by uncertainty humble. There is a difference. Humility in science is not the absence of confidence. It is the presence of precision about the limits of what has been established. And the limit that matters most right now is this: we do not yet have a theory of quantum gravity. We do not yet understand what spacetime is made of at the Planck scale. We do not yet know whether quantum foam is real in the specific sense Wheeler imagined, or real in some modified sense, or pointing towards something so different from our current concepts that the word foam will one day seem as quaint as the word ether. But we know the question. We know with extraordinary precision where the mystery lives. And that is not nothing. That is, in fact, the most important thing science can possess at any given moment, a clearly defined question that current tools cannot yet answer, but future tools might. Here is something worth knowing and worth carrying with you beyond tonight. The Planck length 10 to the negative 35 meters was named after Max Planck, who derived it in 1899 from fundamental constants of nature, the speed of light, Newton's gravitational constant, and his own newly discovered quantum of action. Planck himself described these units as natural units that would be meaningful to any civilization anywhere in the universe, not because humans had decided on them, but because they were written into the laws of nature itself. Think about that. The Planck length is not a human convention like the meter or the inch. It is a feature of reality. It is the scale at which the known laws of physics cease to apply, not because our instruments are too crude, but because the laws themselves in their current form run out. It is a natural boundary, a horizon written into the structure of the universe, visible from anywhere in the cosmos, to any intelligence sophisticated enough to measure the fundamental constants of nature. Any civilization, anywhere in the universe that had discovered quantum mechanics and general relativity would arrive at the same Planck length. They would face the same incompatibility. They would ask the same question. They would look at the same foam or the same absence of foam and wonder. There is something deeply companionable about this. In our search for the structure of space-time, we are not alone in the universe, not in the sense of other intelligent beings we do not know about those, but in the sense that the question itself is universal. The mystery is not a product of human ignorance that a more advanced civilization would have already resolved. It is a mystery written into the fabric of nature, waiting for anyone who looks closely enough to find it. And perhaps that is the most fitting note on which to let this particular night of wondering come gently to rest. We began this evening with a question that sounds almost too simple. Is space really smooth? We traveled from Newton's absolute space to Einstein's flexible space-time, from Heisenberg's uncertainty principle to Wheeler's quantum foam, from the Casimir effect to the Fermi telescope, from string theory to loop quantum gravity to the holographic principle. We visited Copenhagen in 1927, a Dutch laboratory in 1948, a gamma-ray burst 7 billion light-years away, the interior of a black hole, the surface of the cosmic microwave background, and the boundary between what is known and what is not. And at the end of all that, traveling, the honest answer to our original question is, We don't fully know. Space may be foamy. The evidence suggests it is not smooth all the way down. The mathematics demands something happen at the Planck scale. But what exactly happens, what the foam looks like, what it is made of, whether foam is even the right word for it, remains one of the deepest open questions in all of science. Is that a disappointing answer? Only if you came looking for closure. But if you came looking for wonder, and I think at this hour that is exactly what you came looking for, then the open question is the gift, because it means the universe is not finished with us yet. It means there are still discoveries to be made that will change everything. It means the story is still going. Have you ever noticed how the most beautiful stories are the ones that leave something unsaid? The ones that end not with a period, but with a breath, a slight pause, an open space, an invitation to keep wondering after the last page is turned. Perhaps physics at its best is exactly this kind of story. Not a ledger of established facts, but a living narrative, incomplete, sometimes contradictory, occasionally surprising even its authors, always pointing towards something just beyond the reach of current understanding. The space you are drifting in right now, this quiet, dark, apparently simple emptiness, is one of the universe's great mysteries. It holds you, it surrounds you, it separates the atoms of your body and the stars of every galaxy. And at its very bottom, at a scale so small that it has no name in any language except mathematics, it may be doing something extraordinary, something restless, something that no eye has ever seen and no hand has ever touched, and no mind has yet fully understood. That is where you are resting tonight, on the surface of a mystery, in the middle of a story that is still being written. In a universe that after 14 billion years of existence and several hundred years of science still has the courtesy to surprise us. And that, quietly, gently, is enough. Sleep well, friends. Dream of deep things. Let the questions float rather than settle. The universe will still be here when you wake vast, patient, and endlessly beautifully strange. Thank you for spending this night with me, truly. There is something I find deeply moving about the fact that you chose in the hours meant for rest to wonder about the texture of space and the nature of the foam beneath everything. It says something good about you. It says you are the kind of person who has not stopped asking, who has not decided that the world is already explained, who still finds the unanswered question more interesting than the comfortable assumption. If tonight's journey left you with something, a new image, a new question, a small shift in how you picture the space between things, then it did what it was meant to do. Not to teach, but to invite. Not to close, but to open. Not to explain the universe, but to remind you that the universe is worth explaining, and that the explaining is one of the most human things we do. The next story is already waiting, and it lives as all the best stories do, somewhere between what we know and what we cannot yet imagine. Until then, rest gently, wonder quietly, and let the foam beneath you do its ancient, invisible, extraordinary work. Good night.